Hi, welcome back. In this module, we're going to be looking at automated testing within the software development process. So we're going to start off by seeing how we can complement our automated tests with manual testing, and we're going to learn about a specific form of manual testing called exploratory testing. We'll also learn a few different ways that we can get our QA specialists involved in the wider software development process. Next, we'll learn how our automated tests fit in with the continuous integration process, and also the role of automated tests in enabling continuous delivery. We'll get an overview of how automated testing can be accomplished with test-driven development, and we'll also briefly cover some advanced testing tools and techniques. And we'll wrap up the course with some further learning resources. So let's kick off this module by seeing how we can complement automated tests with manual testing. So the first thing to realize here is that automated tests generally don't replace all manual testing. There's a whole class of defects that manual testing might uncover that our automated tests didn't. So in this course, we've learned that we can create unit tests, integration tests, subcutaneous tests, and also functional user interface tests. To complement these automated tests, we can have our QA specialists perform manual testing. Oftentimes, this is done through the user interface of the application, but our QA specialists here might also have access to the underlying system database to check that the correct data is being written or to investigate potential bugs. They may also have access to other files, such as data files or system log files. When we're complementing our automated tests with manual testing, our QA specialists here are probably not going to follow predetermined test scripts. So if our QA specialists here aren't following some predetermined test script, how are they going to test the application? One method they can use is exploratory testing. The Agile Alliance defines exploratory testing as a practice, a style or approach to testing software which is often contrasted to scripted testing. So earlier in the course we saw how we can replace manual scripted tests with automated tests. With scripted testing, these predefined test scripts sit at the heart of the testing process. Our human testers here are simply execution engines for these predetermined test scripts. With exploratory testing, on the other hand, our QA specialist sits at the center of the manual testing process. With exploratory testing, our QA specialist explores and investigates the system. Their job is to understand and learn more about the product. This can involve using the product in completely different ways, or trying to use the product in weird ways. As an outcome of exploratory testing, the QA specialist can report missing requirements as well as probable bugs. They can also look for both predictable and unpredictable outcomes. Essentially, in exploratory testing, the QA specialist can use their past experience with the product to guide future testing, rather than having any rigid test scripts. With exploratory testing, there's less upfront work required, for example, to go and create all of the predetermined test scripts in advance. Exploratory testing can be a lot more intellectually stimulating for the individual QA specialist because they're not simply following a predetermined test script that was written by someone else. Exploratory testing can help generate ideas for future features of the product. It's worth mentioning that exploratory testing done right is a disciplined approach. It's not simply a person randomly clicking on buttons and playing with the software. Exploratory testing emphasizes the freedom and also the accountability of the individual tester. During exploratory testing, when a bug is found, a failing automated test can be written to reproduce it. When the bug is fixed, the test will now pass. In some future change, if the bug reoccurs, it will be caught by the automated test. In this way, exploratory testing can help us identify any missing automated tests. Our QA specialists can add value throughout the project lifecycle, not just in the testing phase. For example, they can assist with requirements analysis and take part in discussions. They may be able to help identify missing requirements or potential testing difficulties with the features that are being proposed. QA specialists can also assist the business analysts, for example, helping the BAs to define the acceptance criteria for a feature that's going to be developed. QA specialists can also pair program with developers when they're writing automated tests. This can help developers identify missing tests or missing test case data. Let's take a look now at how automated tests fit in with the practice of continuous integration, and then we'll see how continuous integration, including our automated tests, fit in with the concept of continuous delivery. Continuous integration is a software development practice where members of a team integrate their work frequently. Usually, each person integrates at least daily, leading to multiple integrations per day. Each integration is verified by an automated build, including test, to detect integration errors as quickly as possible. Part of continuous integration is the execution of our automated tests. Let's start off with our version control system here. So for example, this could be Git. And in this diagram, we've got a dedicated continuous integration build server. We have a number of developers all writing code. So our first developer here commits some code to the version control system. The continuous integration build server can notice this and kick off a new CI build. Our second developer here commits a change to the version control system, and this can kick off another build. And we have our third developer here also committing to version control, and once again this might trigger a build on the CI build server. So typically when a build is triggered on the CI build server, the build server will get the latest changes from version control. It will try and compile or build the code. And if the compilation is successful, we can start off by running our unit tests. Normally we'd want to run the unit test first because they're going to give us the quickest feedback to tell us if the latest code committed to version control is causing problems. We can then proceed to run the slower forms of tests, such as our integration tests, our subcutaneous tests. We could deploy the application or website to a test server, and then execute the user interface tests. These automated UI tests are going to execute more slowly than unit tests, for example, so we wouldn't want to rely on these for quick feedback. Finally, the continuous integration build server can report the results back to the project team. Automation in general and automated tests specifically are key components to enable continuous delivery. Continuous delivery is a practice that allows smaller changes to be deployed to production more frequently in an automated and predictable fashion to deliver value more often and decrease time to market for new features. So for example, we have our developer here committing code to the version control system. As we just saw, the continuous integration build server can notice this commit and build a new version of the software. One of the outputs of the CI build can be the actual executable or deployable binary that may eventually make it to production. This deployable artifact can be stored in an artifact repository. This means that the same artifacts that were created by the CI build server can be installed in the performance testing environment, in the user acceptance testing environment, and also in the production environment. One of the key things that enables continuous delivery is our automated test suite. Without the predictability and quick feedback of automated tests, it's going to be hard to get the required level of confidence in the timeframes necessary to be able to release potentially multiple times per day to the production environment. One thing to note with continuous delivery is that we don't have to automatically deploy every build to production. One technique that can be used when creating automated tests is the practice of test-driven development. Test-driven development, or TDD, is a technique for building software that guides software development by writing tests. There's essentially 3 phases to TDD. The first phase is the creation of a failing test. So before we go and write the production code, we write a test that's going to fail. So for example, if we were adding division functionality to a calculator, we could write a failing test that divides 10 by 2 and asserts that the result is 5. Because we haven't yet written the division behavior, this test will initially fail. In the second phase, we actually go and write enough code until our test passes. So in our case, this would be to implement the division functionality. The third phase of test-driven development is the refactor phase. In this phase, we clean up the code we've written to keep the codebase maintainable and easy to understand. We then repeat this cycle until the required level of confidence is reached and the new features are complete. Some of the benefits of TDD include helping the developer think about the problem or requirement before they go off and write the actual production code. This can help solidify what's required before wasting time and writing code that doesn't fulfill the requirements. Test-driven development can help produce better code designs by evolving the design over time and driving that evolution from the tests. TDD can provide a good work rhythm or flow for developers. The automated test suite that results from TDD can be considered a byproduct. However, these automated tests have a huge benefit in enabling us to find bugs in the future. And also, the resultant tests help document what the system is supposed to do, though this benefit is not specific to TDD. Some of the potential downsides of test-driven development is that it's a skill that the developers will need to learn through practice. It's not something that you can just pick up in half an hour. Another potential downside is that the refactor stage can sometimes be neglected or omitted. This results in harder to maintain messy code. Religious application of test-driven development may result in over-testing. In the previous module, we learned that automated tests ultimately should give us a required level of confidence. This over-testing, the creation of too many tests, can also occur when we're not using TDD. Finally, one of the common mistakes of test-driven development is the over-reliance on mock objects. Though this can be avoided with sufficient practice, and also making sure that the unit of behavior in our unit tests is not too small. In addition to any unit testing frameworks that we may be using, there's a number of advanced testing tools and techniques that can be employed to improve the overall test suite. For example, we can use auto data tools that essentially help us in the arrange phase of tests. For example, the creation of anonymous test data. This is test data that we don't really care what it's set to, only that we need to provide a value for the test to execute. One example of this is the auto fixture library for .NET. Another testing tool that we can add into the mix is approval tests. This is available for a number of different platforms, including Java and .NET. And essentially this lets the developer use their human intelligence to mark a result as complete. This approved result can then be compared to future test runs, and if the approved result differs in a future test run from the actual result, the test will fail. We can employ the concept of live testing during development, so as the developer's writing code, in the background the unit tests are executing, giving us live feedback, showing us if anything is currently broken from the changes we're making. The aim of this is to further reduce the feedback time of any errors that are being introduced. We can also employ code coverage tools. This lets us see the amount of production code that our tests are actually executing. So for example, if we had 80% code coverage on our unit tests, it would mean that we have 20% of the production code that's not being executed during automated tests. So that brings us to the end of this module. In this module, we learned how we can complement our automated tests with manual tests. We learned that our QA specialists, rather than working from test scripts, can perform exploratory testing. We also learned how we can get our QA specialists involved, including during requirements analysis, and also helping the business analysts to define acceptance criteria. They can also pair program with developers to help write automated tests. We learn that we can execute our automated tests as part of a continuous integration build, and how the automated tests in our continuous integration build are one of the things that enable continuous delivery. We got an overview of test-driven development and how it consists of 3 phases: and finally a brief overview of some advanced testing tools and techniques. So that also brings us to the end of this course.